Good morning, everyone. My name is Tong Yang from Peking University, and Zhu Yang, Zhengjie are my students. And Milan and the other authors include Milan from Harvard University, Xiaoming Li from Peking University, and Steve from UK, Queen Mary University. And today my topic is code filter, a meta framework for faster and more accurate stream processing. And here is the outline. First, we introduce the background. Because in today's big data, the big data is often organized as data streams. And in many big data streams, the data comes as high-speed streams, such as phone calls, videos, sensor data, network traffic, web links, and clouds. For the high-speed data streams, you can observe it only once, so you need to process in one pass. And second, the speed is very high, and you need to record each element information. And third, because the stream speed is very fast, it is often difficult and often unnecessary to achieve exact statistics. So, and there are many data stream processing tasks, such as frequency estimation, top key, hot items, heavy changes, super spreader, DDoS detection, frequency distribution, cardinality, and entropy. And there are also other tasks. And in this paper, we focus on the first three measurement tasks. And these tasks are often handled by sketches. Sketches are very popular in recent years. And there are many recent papers published in top conferences, such as SIGMOD, SIGCOM, SIGKDD, VLDB, SDA, ATC, and Infocom. Okay, so and this is a data stream, so we can, for each element, we use a color. And the element with the same color, we can see they are the same element. So each element, or we call it each item, could appear more than once. So and the most widely used sketch is the CM sketch, count me, and we show how it works. Here, when the blue item is arriving, we just compute 4 hash functions to locate 4 counters. There are 4 arrays in this example. Each array is associated with an independent hash functions. And so for this insertion, we just map it into 4 counters and increment all the 4 counters by 1. So this is count. And the query is very simple. For the same element, we compute the same hash functions, 4 hash functions, and we get 4 counters. And the query is very simple. We just report the smallest one, so 80. It means the blue atom appears at most for 80 times. So it had only overestimation errors. And this is count me sketch, the most widely used one, but it's not very accurate. And a simple improvement is called the CU sketch. CM sketch just increment all the mapped counters. But for CU sketch, it only increment the smallest one. If we insert the blue atom again, we only increment the smallest counter by 1. This is CU sketch. CU sketch also has only overestimation error, but it is much more accurate than the CM sketch. And this is for the bio sketch is for the frequency estimation. And the second task is called finding top key hot items, or often known as heavy hitters. For heavy hitters, there is, suppose we have a min heap. And when the data stream arrives, we insert them into a min heap. Suppose the white item appears twice, the gray item appears 3 times, and the blue one appears only once. And and in this case, a red atom appears. The spacing algorithm just kick it out, replace it by the red atom. After this replacement, the initial frequency of the new atom is minimum one is a minimum frequency plus one, because the spacing algorithm thinks because the red one replaced the blue one, so the frequency of the red atom should be larger than the blue one. So it just increments the frequency by one. This is specific, the most popular algorithm for finding top K hot atoms. And this is the first contribution of space-saving. The second contribution of space-saving is it proposes a stream summary data structure to replace this mean heap, because the mean heap, the updated complexity of the mean heap is O log n. But the stream summary, the updated complexity of stream summary is O1. And this is two, but for space saving, it can achieve high accuracy, but the frequency will be largely overestimated. And the third is finding the heavy change. Finding the heavy change, suppose we have two time windows, and we can just build two mean heap. And then we will find the gray one appears 4 times in this window, but in next window, it appears only 1. So the difference, when the difference exceeds a threshold, we call this is a heavy change. And simply we can build two space saving and compute them and compare them, and then find the heavy change. But because the frequency of space saving is very inaccurate, so there is a better algorithm called Florida, published in NSDI, and it is more accurate, but it needs to record all the frequency, so it is still not memory efficient. So this is a limitation of state art. They just mixed the cold atom and hot atoms. But actually, in real data streams, the frequency distribution is highly skewed. It means the majority is cold atoms. It appears only once or twice. But there is very few atoms appear many times, and we call the hot atoms. But it is minority. For the counting sketch, we need to let each counter large enough to store the frequency of the hot atoms. So because the hot atoms is very few, so it is not memory efficient. For the space saving, each cold atom will enter into the mean heap, increment the frequency by 1. So it will lead to poor accuracy for space saving. And the recent work called augmented sketch, published in Sigmodal, and it used 2 stages. The first stage recorded the hot atoms, and the second stage recorded cold and hot atoms. And then frequent exchange between the 2 stages to keep track of, to make the hot atom very accurate. It used just one array, so the array cannot be very long. The authors recommend using only 32 atoms in the hot atoms in the first stage. So this is a 2-direction exchange. It cannot be implemented in hardware. And next we propose our solution. Our solution includes 2 techniques. The first technique is called a cold filter. The second is called aggregation and evict. And this is our framework. The first stage is called a cold filter. We just filter the code in the first stage. And in the second stage, we only let the hot atoms enter into the second stage. We can use sketch, specimen, and Florida in the second stage. And here we can use the quantum mean of the CU. We can use the quantum mean of CU in the first stage to record the frequency of cooled atoms. And we can use small counters. In this stage, we can use very large counters. For specimen, because the cooled atom will filter by the first stage, it will not enter into the specimen, so it will be more accurate. And for Florida, we don't record the information of cooled atoms in the Florida because the cooled atom is filtered by the first stage. So in this way, we can improve the memory efficiency of Florida a lot. And this is the data structure of our cooled filter. We can just use two layers. Each layer is a CU sketch. And to achieve high speed, we just confine the key hash functions into one machine word because each counter can be very small. For example, only 4 bits. And we can use the second layer. Actually, we can use one layer or second layer. We use two layers to achieve to achieve memory efficient. And when the counter overflow, we just keep it we just keep it unchanged. It means if it's 15 and 4 bits means that this is the maximum value. We just keep it unchanged. It means we need to access the second layer, the second layer. And next is our aggregation and evict. In this example, there's a data streams. And if we just insert into the quantum mean sketch, we need 8 insertions. Each insertion into quantum mean of Florida, we need multiple memory access. And if we aggregate them in advance, suppose the blue ones appears twice, we just we can just insert these 3 atoms by only 3 insertions. And in this way, ideally, we can achieve 2.67 speed up. But the problem is how to design an efficient aggregator. And this is the data structure of our aggregator. We just use a hash table. Each hash table is composed of many buckets. Each bucket have several cells. Each cell and this is cell. Each cell stores a key value pair. Key is is item ID. Value is frequency of its flow ID. And when this bucket full, we just kick one out and to the cooled filter. And because we want to achieve very fast speed, we just randomly choose one to kick it out. And this is because for each insertion, we need to check whether the incoming item appears in this bucket. We use SIMD to achieve more to achieve faster queries. Okay, and then next is our experimental results. And we use 3 data sets. The first is IP trees, the second is web page, and the third we write a program to generate synthetic data sets. And next is a computer. And we apply our cooled filter to CM sketch. In these experiments, we apply our cooled filter to CMCU sketch. And we found that when we vary the size of cooled filter, we found the average absolute error of sketches when using cooled filter is much lower than other sketches. And this is and this is the insertion speed. If we when we vary the memory usage itself, we found that the insertion speed almost unchanged. And this is the experiments on top key hot atoms. And we use the same memory for all algorithms. When we vary the key for top key, because when the memory is fixed, if we and if we increase the value of key, the accuracy will drop. And we found that the accuracy when using our code filter keeps almost unchanged, but our algorithm will drop significantly. And the insertion speed is also very much faster than other algorithms. And the third experiment is on the heavy change. And because flow radar is more accurate than speed saving, so in these experiments, we compare the flow radar before and after using our code filter. And for the two different data sets, we found that after using our code filter, the memory is significantly reduced. Because in these experiments, we let all the data structures to achieve the same precision, 99%. And the insertion speed is also significantly improved. And this is a summary of our experimental results. The speed improvement is up to 4.7 times, and the accuracy improvement is up to 41 times. And in our paper, there are more than 50 experimental figures in our paper. And we will apply our code filter into more sketches in the future work. So then this is the conclusion. We propose a framework can be applied to many sketches and have two key techniques. First is code filter. Second is aggregation and evict. The code filter just filters the code and to let the second stage to handle the hot atoms. And it is generic. It can be applied to many measurement tasks. It can improve the accuracy a lot. The second technique can accurately aggregate atoms so as to improve the speed a lot. All the source code are available at the GitHub. So that's all. Thank you. Okay.